Assalamualaikum warahmatullahi wabarakatuh, and hello everyone. My name is Fairus from University Teknologi Malaysia, and today I will present the work on carbon nanotube synthesis. We are doing both the experimental work and the modeling work, but for this presentation, I will focus on the modeling part of our project. So this is on the development of multi-scale model for prediction of carbon nanotube growth in flame environment. Okay, what is carbon nanotube? It's basically a cylindrical structure, or in particular tubular structure that made of carbon atoms. It's very small, and you can see it will be like a black powder with the naked eyes. Under the microscope, it will look as tubular structure. Some of them with multi-wall, some of them with a single wall. But for our project, we are focusing on the multi-wall carbon nanotube. Yeah, so like I said, the building block of this carbon nanotube is carbon atoms that we can get from the carbon source like methane, ethylene, and so on. Okay, so in brief, carbon nanotube is a strong material. It's 100 times stronger than steel. It's very conductive, so 100 times more conductive than copper. And in terms of the heat conductivity, it's also outstanding in terms of copper as the thermal conductor. Okay, however, the price is quite expensive, and the reason being is because the synthesis process is not cheap. So carbon nanotube, because of the outstanding mechanical, electrical, and thermal properties, it can be used to improve the performance of the end product. For example, for composite product like the frame of the bicycle, your racket, the tennis racket, okay, and so on. You know, it can be strengthened by using carbon nanotube as additive in these composites. Yeah, so due to the high conductivity, it can improve also the performance of transistors in the computers, in the batteries, and also in the smartphones. So conventionally, carbon nanotube is being synthesized using furnace. So this is what we call the chemical vapor deposition method, which basically use the furnace for throughout the period of the synthesis process. So it is highly energy demanding, and then this is actually the way of mass producing the carbon nanotube. It tends to be slower in the whole process because it involves the artificial breakup of carbon atoms. So on the left is the conventional method, which is available now, but it's expensive. Yeah, so now our research is trying to cut down on the cost, by introducing flame. From the flame, you can basically get both the heat and also the carbon source. Because the flame is sustained with hydrocarbon stream, what we call fuel from in the combustion community. So it will be lower cost because you get both the heat and also the carbon from the same stream of the hydrocarbon. And then it's much more rapid because within flame, you have natural breakup of carbon atoms. It will be much more faster compared to what you see in the artificial breakup of hydrocarbon. And this is will be less energy consumption because you cut a lot on the synthesis time. Okay, so in terms of the any synthesis of carbon nanotube, you require the heat, the carbon source, and also the catalyst. Yeah. So with flame, we basically have the heat and also the methane as the carbon source. And you can see on the right there is a simple burner where we basically use the traversing system or traversing arm to put the catalyst into the flame, and within minutes you will start to see the carbon nanotube if you put it under the microscope. And then we have this wire mesh as our collector. So basically we deposit the catalyst on the wire mesh, and then we put that inside the flame. All right. So flame using flame to produce carbon nanotube is a great idea, but it comes with some challenges. The whole environment of flame is heterogeneous. That means you have a lot of high temperature gradient, and high carbon source gradient as well. So you need to know exactly where within the flame to get the optimum growth of carbon nanotube. Therefore, we will basically introduce this modeling work to help us to identify the optimum region of growth. All right. So there are various parameters involved in the flame synthesis. You have the location within the flame, you have the inlet conditions of the burner, the type of the fuel, the type of the catalyst, and so on. So all these various parameters need to be studied, and so that we understand how that affects the whole synthesis process. In the flame, you cannot independently control the heat and also the carbon source, unlike what you see in the furnace. In the furnace, whatever temperature you like, you just turn the knob and then you will get the temperature that you want. In flame, the temperature control is not that straightforward. But however, we can introduce a different method to control the synthesis process that will produce, a well-controlled synthesis environment. Okay, and in terms of the modeling work, a comprehensive model that can cater or that can model all the process that happens within the flame synthesis is not yet available. So therefore, now we introduce this multi-scale model to assist the modeling community in terms of the modeling of CNT synthesis in flame. Okay, so we are introducing multi-scale model, and the reason why we call it multi-scale because we basically working with two different scales, which is the scale of 1 meter to 10 to the power of minus 2 meters. So this is what we call the flame scale, and then lower than that, all the way until 1 nanometer, you have a particle scale. So basically, the flame will be modeled using what we call CFD, computational fluid dynamics, that will solve for the temperature and the mass fraction within the flame, and then we will couple that flame model with the particle scale model, what we label as growth rate model, that will take the temperature and the mass fraction from the flame model. So this will be the input temperature and mass fraction, and it will be put into this growth rate model that will produce or the prediction of carbon nanotube length and also the growth region within the flame. Yeah, so this is when we couple both the two models, we call it a couple model or multi-scale model. Okay, so in terms of the growth rate model, it captures all the physics, or all the important physics that involve within the catalytic growth of carbon nanotube using ordinary differential equation. Yes, so you have adsorption, desorption, diffusion, and then cluster formation prior to the CNT growth, or it will ended up with catalyst deactivation where the carbon nanotube growth will basically stop. Yeah, so all these are basically put mathematically or explained mathematically by this growth rate model, and we are assuming that the catalyst is present throughout the flames, okay, and the surface breakup of the catalyst is excluded from the model. And what surface breakup is basically the formation of catalyst particle as the catalyst surface is exposed to the high temperature environment. Yeah, so you can see here that first the carbon atoms will be adsorbed into the catalyst. Yeah, so here, and then some will be adsorbed and some will be dissolved away from the catalyst surface, and those that is adsorbed, it will be diffused, what we call bulk diffusion into the catalyst, and then it will start to produce the nucleation process or the cluster formation that will be the base for the CNT formation. Yeah, and then depends on the rate of diffusion and also the rate of adsorption of the carbon atoms on the surface of the catalyst. You may have the catalyst deactivation where the catalyst surface will be deactivated and it will basically reduce the rate of the growth and finally stop the growth. Okay, so in terms of the flame model, we are using computational fluid dynamics with flamelet solver, and we basically modeling the. We have two ways of modeling this. One is using simple chemistry approach, and another one is using detailed chemistry approach. Yeah? So DC is for detailed chemistry, and SC is for single chemistry. So for detailed chemistry, we have 53 species with more than 300 reactions. We solve using mixture fraction method. Therefore, there are only four governing equations other than continuity and the energy equation. We are solving the mixture fraction and also the other flamelet equation. And then for simple chemistry, we are having seven species. Okay, therefore, other than the three main governing equations for the fluid dynamics, we also solving seven species equations, species transport equations, and we basically have the total of 10 governing equations. Okay, so there are only two reactions involved here. Okay, so in terms of the solver, yeah, so it consists of two parts. One is the production of the flamelet library, yeah, based on the number of species that you solve for detailed chemistry, yeah, and then it will basically produce the PDF function to explain mass fraction of the species and enthalpy as a function of mixture fraction and mixture fraction variance, and then this will be compiled in a library that will be read, either online or after the end of the CFD solution process. Yeah, so this library will be coupled with the CFD solver to produce the prediction of species distribution within the flame. Okay, so the geometry that we have is basically a simple burner. Yeah, so it has this is what we call inverse diffusion flame, where fuel is at the outer annulus. Yeah, so you have fuel inlet at the outer annulus. This is the zero is the center line of the flame. So within the central tube, you have the oxidizer stream, and then the fuel stream is in the outer annulus side. So in terms of the geometry, so the size is mentioned in this slide. Okay, the fuel composition consists of mixture of methane, ethylene, and then for the air you have nitrogen with oxygen with 70% and 30% by volume, and then the flow rate is identified as 0.2 meter per second at all the inlets, yeah, to avoid any shear between the stream. Okay, so now we want to compare between how good the single chemistry prediction, simple chemistry prediction with the detailed chemistry prediction. Therefore, what we do is we compare the predicted temperature and also the predicted methane concentration within the flame using the model that we have. Okay, so the solid line here is basically for detailed chemistry, and the dashed line is for the single chemistry. We start with the left figure here. This is the figure of temperature versus radial location. So there are basically two different height above burner involved here. Yeah, so when we say 13 millimeter height above burner, that means it's 13 mil. The reading here is taken at 13 millimeter downstream of the burner. Okay, so you see that the temperature in the experiment, in the measurement of the experiment, it shows that the temperature is higher towards the center line of the flame. Yeah, so R equals to 0 will be the center line of the flame. So as we get closer to the center line of the flame, the temperature is measured to be higher there. Okay, so in terms of the single chemistry prediction, yeah, you see that the general trend is pretty much agree with the experimental measurement. However, if we take the average error for the temperature prediction, we see that the detailed chemistry model is producing much less error compared to the single chemistry model. Yeah. So if we look at the DC model here, when we compare the predicted methane concentration with the measured ones. Yeah, so you see that the measurement of methane concentration shows quite you have a small concentration close to the center line, and then it gets higher away from the center line. Okay, and there are slight differences at various heights above the burner. Okay, for single chemistry model, it basically showing that the maximum value of the methane concentration is further away from the center line of the flame, in contrast to what is being shown by the experimental measurement, where the maximum concentration of methane is actually somewhere closer towards the flame center line. So for DC model, you can see it better predicts the trend. So you see that the improvement of the carbon source prediction is 15% to 25% at various height above the burner by using detailed chemistry model. So overall, in terms of the prediction of temperature and also the mass fraction of the methane, you see that detailed chemistry model is performing better compared to the single chemistry ones. Okay, so we see here that the chemical modeling within the frame is quite important. By including, more detailed reactions, into our model, we see that it improves the thermochemical prediction of the flame. Okay, so now let's look at how good the two models in terms of the prediction of the growth region. Okay, so what we call growth region is where is the location within the flame where CNT was found to be abundant. Yeah, so there is a certain threshold in terms of the length of the carbon nanotube that is set in the experiment. Whenever we get the images taken at various the images of carbon nanotube that is grown at various locations within the flame, we set a threshold of the length. Okay, and then we will define the growth region accordingly inside the within the experiment. Okay, so the black band here is basically the experimental growth region. That means based on the post processing of the microscope images, we come up with the measured growth region in the experiment. And then the dark gray band here is basically for the prediction of growth region using detailed chemistry, and the light gray band is basically for single chemistry model prediction. Okay, so they are basically two high above burner here. The top one is 13 millimeter high above burner, and then the bottom one is the prediction of growth region at 18 millimeter high above burner. And you see here that the two showing that we have growth region. Growth region in the experiment is 5 millimeter to 9 millimeter at 8 millimeter high burner, and then further upstream you see the experimental growth region shrinks a bit, yeah, but it falls more or less within the same range of the location within the flame radially. Okay, in general, you see that the DC model agrees much better compared to the single chemistry model. Yeah, so you can see that the average error of the single chemistry model is much larger compared to the DC model. Okay, so and for your information, the error that is determined here is basically based on the comparison of the boundaries of the CNT region on the left and also on the right with the actual ones come from the experiment. Okay, other improvement in terms of the growth region prediction is the fact that with the detailed chemistry model, we don't require any artificial boundary. Yeah. So in the multi-scale model, what happens with the prediction of length? We basically take the threshold with respect to the maximum length. Let's say here we use 70% as the maximum length. So this value has been decided based on the comparison with the microscope images of at various growth region within the flame. Okay, so by using this, if we don't put any artificial boundary, so you can see that the prediction of the growth region is much over predicted. Yeah, that means the length of the growth region is over predicted so much compared to the experiment. To repair that, so we're basically using an artificial boundary by using a correction factor to the length of the growth region that is predicted by the multi-scale model, and then that produce a much shorter growth region, and this will basically make the growth region within that is predicted by the single chemistry to be more reasonable. Yeah, so you see the top one is the prediction with artificial boundary, the bottom one is without the artificial boundary. And the modeling, the prediction of growth region is much more physical using the detailed chemistry model without introducing any artificial boundary. So the bottom one is basically taken at different height of Werner. So you see that with 70% maximum length threshold in the model, we more or less reproduce the growth region shown in the experiment. Okay, other than that, we can see that improvements on the physics of the CNT growth, okay, where the detailed chemistry model improved the physics of CNT growth location to be physically predicted at the fuel site. So you can see CNT length here for the detailed chemistry model is predicted on the fuel side compared to on the oxidizer side. So we expect this to happen because we saw this in the experiment. Okay, in terms of the surface density of carbon atom, you can see that surface density of the carbon atom is much more higher on the fuel side when we use detailed chemistry, but the single chemistry seems to not reproducing the physical trend of the distribution of the carbon atoms. Okay, in conclusion, we're quite happy with the multi-scale model that we have developed with the improvement up to 10%, 25%, and 50% when we switch from single chemistry to detailed chemistry model. So this improvement that I meant is basically in terms of the flame temperature prediction and the carbon source prediction. So detailed chemistry produces corrected physics, but the single chemistry does not produce the corrected physics. So I think that's all. Sorry to take a bit more time. Thank you very much. Assalamualaikum, and have a good day, everyone. If you have any question, we can check in the online session.